Okay, I'm going to do a little bit of a walkthrough from Octave. And I'm kind of picking some things out of the introduction to GNU Octave that is one of the guidebooks here. And so I'm going to use some things in it. What I'm immediately going to do here is I'm going to go into my window and I'm going to show the editor. And I want to use the editor to do a lot of my work. And so we can make what are called .m files. And what .m files do is they run all of the tools, all of the commands in them as if it was on the command line. So I'm going to take some of the things that we see in the book, and I'm going to do it in an M file. So if we're running a script, a MATLAB convention is to have a 1 semicolon in front to distinguish a script from a library file. This won't really affect most things we do, but it's just a convention to have in, and if you need MATLAB compatibility, it's just good programming practice on it. What I'm going to do here is I'm going to make I'm going to look at some of the examples in the book on the command line, and then we're going to see how we can do some of the things in the script. So as a calculator, there's 6 divided by 2. Here's 6 divided by 2 plus 3 times 7 minus 4 to the second power. And so we have a calculator. But what really makes our calculating functions work is MATLAB and Octave are inherently used for matrices. And so if I type in braces between a list of numbers with no dividers, notice that makes a row vector. It prints out in the display a row vector. I'll make my window here. So I'm using the command line. I have u equals, and over in my command history, I can see the commands I've done. And if I come back up, there's now a variable stored in my variable editor over here on the left-hand side. So there's a variable u. It has the dimension 1 row by 1 by 3, 1 row by 3 columns. And then in my answer from the previous calculation is also stored in memory. We can always refer back to previous answers just like your calculator can. And the editor for Octave lets us see these things. I think if I look at my variable editor, yeah, it will actually show me the value that's inside of this. If I scroll all the way over, I can see the value that's inside of the variables. So as you're working with something and you're not getting the results you want, you can look at what's happening to your variables with the values. Kind of like some advanced debuggers for other computer languages. But again, we're just going to use this as an extra fancy calculator. And I'm kind of going through 1.3, the basic arithmetic and matrices and vectors option in our intro to GNU Octave. So here, by putting a semicolon at the end of each entry, and that's actually a semicolon will tell me when I have the end of a row, I have made a column vector. And if we notice, the dimensions have changed on my u vector. And I can also make a matrice. So here's the first row, here's the second row, and here's the third row. And so there I have a 3 by 3 matrix, which is also stored in my memory. Now we can do vector operations, and we can assign variables inside my editor. So right now, up in my file browser, it's saying my files will be stored in home J. Thompson. So what I'm going to do in here is I want to find a directory. I'm going to go to Documents. I'm going to go to Fall 2025, and I'm going to go into Mat 220 because that's this class, and then I'll put a place for Octave scripts. So all my stuff, I'm going to work from here. This is going to be my working directory. And I'm going to create a file. So for right now, I think, what is this? This is, I'm going to save as chapter 1, section 3 .m. And so I get a chapter 1, 3m in my file lists. And so what I'm going to do with this is I'm going to put in procedural things that I use often. In my case here, I'm going to store a vector. So I'm going to store u in my script. And if I don't want it to be displayed to the screen, I'll put a semicolon at the end. So let's look at a difference here. So I'm going to come over here and I'm going to save my file. Come over here and save my file. And I'm going to switch to this directory. And I think I'm in, let me see if I'm in it. So if I type in the script's name, chapter 1_3, it runs the script. And it outputted the vector. This is doing the same thing as if I typed this on the command line. So these are called scripts. If I put a semicolon after it, that suppresses the output to the screen. When you're doing a lot of variables and subcalculations, and so we get nothing to the screen. So if we're doing a lot of variables and subcalculations, it's not always good to have every step put to the screen. Let's see, so I'm going to do u as this vector, and let me create another vector in my script. V equals 2:1:-1. And so now I have two vectors in the script. I can do calculations with these vectors. In fact, what I'm going to do is I'm going to put, I'm going to call some vector w is going to hold the output of 2 times vector v plus 3 times vector u. It's going to make a linear combination of vectors v and u. And I'm going to store the result in vector w. And I'm going to let this display it to the screen. And so I get the output of doing this vector manipulation. Now vectors have some things that we can work with. First off, we've already talked about the dot product of a vector. So I can show a dot product. I'll make dot product A because it's a scalar. So what I'm going to look at here is the dot of u and v. So you multiply, right, the dot product. If we did it by hand, we'd do 1 times 2 plus -4 times 1 plus -6 times 1. So I'm thinking we would get something around a -8. So let me save this and come down to my command window and rerun chapter 1:3. And so A is a dot product. Now, scripts will become a place to do things. Notice I've run the script, but the things are still in memory. So if I want to look at vector u, on my command window down below, I type in u, and it will print what has been in memory for me. So I do get the ability to see what is happening with u. All right, let's look at some other vector operations. If you're in physics, you have started to see a cross product. You'll see more cross products when you start doing things like torque, because cross products work on the concept of torque. But the way that you would find cross products in physics, you used a determinant of a 3×3 with the top row being the coordinate of the ijk vectors. But let's do a cross product of u and v. And we get the cross product as an answer. So We will define a cross product very well in chapter 3. The cross product is a vector that lies perpendicular to the plane that the vectors u and v make. So a cross product is a way of finding a normal vector, or a norm. If two vectors can define a plane, then in the cross product is the norm to that plane. And finding norms for the people in Calc 3 is important, the normal to a surface. There is also something we're going to call a norm in the vectors. Again, we'll do this in chapter 3. For us, a norm is another way of saying the magnitude. So I can find the magnitude of vector u, and this finds the Euclidean norm. Square each component and take the square root of the answer. And this means we can create a unit vector that points in the same direction. So I can take that cross product. So I can take, I can make a unit vector in the direction of v by taking v divided by the norm of v. And what I've done is, by dividing the vector by its length, I have created a vector of length 1. And that vector of length 1 points in the same direction as v. So these commands really quickly give us the ability to manipulate some different things that we can do with vectors, which we are going to be exploring in the upcoming chapter. And there are other functions that we can do that involve the dot product and the norm, like taking projections onto the vectors, and we'll look at those operations here. So we're going to spend chapter 3 and 4 diving into vectors. Chapter 3 we'll do vectors in 2 space and 3 space. The spaces we're normally used to dealing with because they're geometric. And then we're going to take all those geometric arguments and we're going to be able to deal with vectors in an n space. And what is a 26-dimensional geometry for all intents and purposes if we have a 26-dimensional vector, and how we can mathematically operate on those things. And Octave will happily go with us as we increase our dimensionality. So we have a tool that is not just grounded in Euclidean and non-Euclidean geometries, it's grounded in these abstractions that we're trying to build. But let's do some work with matrices here. I'm going to come back up to my editor window. And I'm going to add some things into this program. I'm going to add a matrix A stored in variable A. And the matrix is going to be 1, 2, -3 on the first row, 2, 4, 0 on the next row, and 1, 1, 1 on the final row. And for right now, I'm going to save that and look at it. So I'm going to come here and run this. And the only thing it should print from the chapter 1, section 3 is matrix A. And I get matrix A here. Now sometimes we're going to create some very large matrices. In your first homework, there is the heat on a plate problem. And that heat on a plate problem, I think I asked you to make a 10 by 10 matrix. By the time we're done with the course in its entirety, you should be comfortable creating a 100 by 100 matrix to get a finer mesh model of that, and comfortable with the mathematics that goes around that. We start with a 2 by 2, and then a 4 by 4, and a 10 by 10. Sometimes that can be a bit odd to read in the editor up here, but notice what I can do here. By using tabs, I can get my matrices to visually look well in the editor, and it doesn't change how they've input. So the editor in Octave and running the scripts are white space neutral-esque. You'll see that some things we do with loops and other constructions, we need to mark our beginnings and ends clearly on them. But it is good to come in here and create things visually pleasing. So I'm going to create matrix B here in my editor. So I have 2 matrices that I can use. Matrix B has 4 columns. I have to make sure I hit my square bracket. And so I can tab my way over. And there's matrix B. I'll save this. And I'll rerun this file, and I should see both A and B. Notice I haven't really cleaned out my memory space here, and so A and B are still in memory. If I remember correctly, it's clear space all clears the memory. In Mathematica, there's no space in it, so that's why I forgot the space. But a clear space all clears memory. But if I come back and run the script, everything reappears in memory. And I do have access to that in memory. So let's see, V was a 3 by 1, so I can do a matrix multiplication of A times V and get a vector answer back out of it. So we do have this ability to do matrix calculations. Now I want to come back up into my script here, and I'm going to put semicolons so it doesn't put the output of A and B on things. And we're going to look at some matrix operations. And so the first thing I'm going to look at is A is a 3 by 3 and B is a 3 by 4. So A times B should be defined. A times B. I'll define it down here. And we get the multiplication of the vectors. Or I'm sorry, of the matrices. But if I reverse the order of multiplication, it is not defined. And the warning message in Octave does talk about dimensionals. It says it puts the first operator is a 3 by 4 and the second operator is a 3 by 3. And we know that these are not able to do matrix multiplications. But I can multiply the transpose. And I don't know if you noticed, I did a post on finding the block matrix of the quick inverse we did based off the question in class. And in my notation for typing, I said I was going to use A prime for A inverse. And I made really clear on that note that I put out, this was just for typing purposes. Because in Octave, transpose, I can do B transpose as a prime. And now my multiplication is defined. So Octave allows B transpose, and I also believe, forgive me if I'm wrong here, that it takes the transpose command also. You can write out the word transpose and get the transpose of B. So that's why I cautioned prime is not a normal notation for an inverse. I was just using it to type that note out really quick. But in Octave, prime is used for the transpose. And so we can do some different multiplications that way. So I have an editor here. It has some variables stored in it, and I might be able to play with those values. An identity matrix is a useful thing, and identity matrix, they're square, and the size of the square determines what the matrix looks like. And so Octave has a really nice command for that. It's I 4 gives me a 4 by 4 identity matrix. So we can create an I matrix of any size we need, or an identity matrix of any size we need, with the I command, but it's EYE to distinguish it from the imaginary number. So I can look at that part of the eigenvectors in the eigenequation that we did. I'm going to put it here. Right, I have my variables stored up here. So notice I'm using my script right now to store variables. So I have variables stored in my script, and I'm coming down to the command window and I'm playing with the variables that come out. So 2 times A minus 4I times 3. Mathematically, this is 2 times the matrix A, and then this is going to be a matrix that has a diagonal of 4s across it, because 4 times the I. And when I do that, what did I? Oh, I forgot to type in multiplied. My bad. And so if I look at what's happening here, the first part is doing 2 times A, and then I'm subtracting from that 4 times I3, which is the identity matrix scaled up to 4. So we get some useful calculating tools. Some other commands, we can find the determinant of A, and we can find the inverse of A. I can find the eigensystem of A, where it lists my eigenvalues. Now, this system has 3 eigenvalues because it's a 3 by 3, and one of them is real because there's a 0 in the imaginary part, and 2 of them are complex. In differential equations, this would refer to something. It has a positive real eigenvalue and negative, so this system is going to be spiraling away from a fixed point, right? There's meaning in this, and we'll work those way through. I'm going to add some other commands that we can do with matrices, which we will develop the concept of the rank of a matrix. And so the rank of matrix A determines how many solutions, unique solutions it can have. We'll see that the rank relates itself to its invertibility, to how many parameters it can make if we're trying to find all the solution sets in it. So rank is a way of classifying the matrix, and we'll see in chapter 5 or 6, we'll develop a good definition of rank. But rank is a command that has a measure on it. So we've definitely got eigenvalues, which we've learned about. Inverses, determinants. Rank is the new thing. We have matrix multiplication and matrix addition. We have multiplication by a scalar and multiplication by matrices. So all of those things are an octave coming through. I'm going to pause this here. I'm going to stop this here. And I'm going to do a second part where we look at plotting and getting things to the screen.